Welcome to Unit 9. In this unit, we will learn about the second big idea in calculus, integrals. This is 9.1, Accumulations of Change. In this lesson, we will be figure out areas of rectangles, trapezoids, and maybe triangles. So if you don't remember, here's a review of the formulas. You can take a look at them yourself. So accumulation. What does accumulation mean? Accumulation just means adding more and more. So if we are saving more and more money, we are accumulating money. Here's a video of there being more and more snow on the ground. So in this video, we have accumulating snow. As more and more snow falls, we'll see that the amount of snow goes up. The height of the snow goes up. So we're seeing more and more and more of the snow. In this lesson, we will know the rate of change of the change. For example, we know how fast the snow is falling. See, the snow is falling really quickly now, and the snow is accumulating really fast in the video. And if we know the rate of accumulation, we won't know how fast the snow is falling, we can figure out how much snow there is. So that's accumulation. So let's look at some examples. Example 1, Introduction to Accumulation. Peterson saves $5 every day. How much money will he accumulate after 8 days? Well, you might say, well, that's just 5 plus 5 plus 5, 8 times, right? Plus 5 plus 5 plus 5 plus 5. There are 8 fives there because it's 8 days. So it's $40. Of course, a faster way of doing that is just $5 times 8, which is $40. So the answer is after 8 days, Peterson accumulates $40. But we can also use a graph. Here is our function. Let's go to decimals. Here is our function for the rate of change. How fast Peterson is accumulating money. The function is just y equals, or a of x equals 5. Because he saves $5 every day. To figure out the accumulation looks like this. The accumulation is the area under the graph of our rate of change, which is a of x equals 5. So the accumulation is really just this area. This is the accumulation. The area under our graph, a of x equals 5. Well, given that a of x equals 5 is a straight line and is constant, the area under the graph is a rectangle. It's a rectangle with length 8 and height 5. So the area, length times width, is 8 times 5 equals 40. You can also just count how many squares are shaded. 1, 2, 3, 4, 5, 6, 7, 8 per row. There are 5 rows, so the area shaded is equal to 40. Okay. So the area of rectangle is $8 times 5 rows, which is $40. In other words, accumulation is also just equal to the area below the graph. So accumulation is the area below our function. Okay? Example 2. In this example, it's going to be a lot harder. We can't just multiply. However, using the idea that accumulation is the area, we can solve this problem much more easily. So here is example 2. Tran is learning new English words. The rate at which she learns new words is given by the function L of t is equal to 2/3 t plus 5 where T is equal to the number of hours she has studied, and L is equal to the number of new words she has learned. Okay. A. How many new words did Tran learn in the first 3 hours? So from 0 to T, between 0 and 3, or 0 is less than T is less than 3, how many new English words did Tran learn? Well, um, this is not constant. The number changes. It goes up over time. So let's look at our graph. Uh, let's graph b of x is equal to 2/3 x plus 5. That's the rate of change. That's how fast Tran is learning new words. So she's learning faster and faster. She's becoming a better student. She's getting faster at learning new words. Again, how many words she has learned is the accumulation. The accumulation is just the area under the graph. The area under the graph is a trapezoid. We can either use the formula for the area of a trapezoid, or we can just divide up the trapezoid into a triangle and a rectangle and calculate that way. Either way works. Okay, part A. How many new words did Tran learn in the first 3 hours? Well, first 3 hours, instead of going from 0 to 9, let's go from 0 to 3. So here's the first 3 hours. How to find this area? I think it's actually easier to just use the rectangle and the triangle. So let's just do that. Let's do the rectangle first. The length, we're going from 0 to 3, so the length is 3. The height is 1, 2, 3, 4, 5. So the rectangle has area 15. Triangle. Triangle, once again, has length 3. The height is 2. So the area is 3 times 2 divided by 2, because it's the rectangle. The triangle here is half of the rectangle, so it's 3 times 2 divided by 2, which is 3. So the total accumulation is going to be equal to 15 plus 3, which is equal to 18. Okay? So how many new English words did Tran learn? Well, we have a rectangle with area 15, and a triangle with area 3. So accumulation equals how many words? Equals 15 plus 3, which equals 18 words. So how many words did Tran learn in the first 3 hours? 18 words. Okay. Next. Let me take a screenshot of this. Next, part B. How many new English words did Tran learn in the first 9 hours? So we're going from 0 to 9 this time. So let's go back to 0 to 9. So we want this area. It works very similarly. Again, our rectangle is going to be 9 this time because we're going from 0 to 9. The height of the rectangle is 5 this time because we're starting at 5. The height is still 5, so it's 45. That's the rectangle. Next, we have the triangle going. The triangle has a length of 9 and a height of 1, 2, 3, 4, 5, 6. A height of 6. So the area is 1/2 of 9 times 6, which is 9 times 3, which is 27. So the total area, the total accumulation is 45 plus 27, which is 72. 72. Okay? So going back to our question, how many words, the new words did Tran learn in the first 9 hours? It's going to be 45 plus 27, which is equal to 72 words. Part C. How many new English words did Tran learn between the hours 3 and 9? That means 3 is less than t is less than 9, the interval 3 to 9. Well, she learned 18 words in the first 3 hours, 72 hours in total. So after the first 3 hours, she learned 72 minus 18, which is 54 words. So we know it has to be 54 words. Okay. If we look back at the graph, what we're saying is we're doing this part minus this part. So we end up with this. This is the area that we're working with because the first part went away. Okay. The easiest way is just to subtract 72 minus 18, and we get 54. We can still do the area of the graph from x equals 3 to x equals 9. We can do that. If we do that, the area of the rectangle is 6 times 7, which is 42. The area of the triangle is 6, is 1/2 of 6 times 4. Okay, 24, which is 12. So the total would be 54. Okay, if we go back, see, 54. Okay, so what did we do? Really, from the first 3 hours, we have this area. The first 9 hours, we have this area. So from hours 3 to 9, it will be this area. Okay. All right. Now, accumulations can be positive or negative. As we saw earlier, you can have more and more snow. That's positive accumulation. But we can also have negative accumulation. Snow will also melt. It will go away over time. So here's a quick video of snow going away. When we have less and less snow, the snow will be melting. When snow goes away, the height of the snow goes down, as we can see in this video. And when that happens, we have negative accumulation. So what we need to be able to do is, if we know both the rate of positive and the rate of negative accumulation, we need to know the net amount over time. Here's an example. We have a water tank here. We have a water tank. Water is flowing in and out of the tank. Water is coming in here. Water is also flowing out of the tank. Water is leaving here. So water flows into tank. That makes the amount of water go up. Water flows out of tank, makes the amount of water go down. So here's our question. Example 3 is on net change or net accumulation. Water flows into a tank over time. This is given by the function a of t is equal to 3/5 t plus 4 for t between 0 and 6. The unit of a is milliliters. It's really milliliters per second. That's the rate of flow. How many milliliters every second? The unit of time is seconds. Water also flows out of a tank over time. This is given by the function b of t is equal to 4/5 t plus 1. Also for 0 is less than t is less than 6. The unit of b is also milliliters per second, and the unit of time is seconds. Part A. If we have 30 milliliters of water at t equals 0, how much water is there at t equals 6 seconds? Well, here's our here's how much water is coming in. The blue, let's go to decimals. The line here, the blue line, is the rate of water entering. So the area is the amount of water that came in. Okay. Next, we have orange is the amount of water leaving, the amount of water going out. So the area is the amount of water that has gone out. Putting them together. So we know the blue part the blue area, which is all of this, is the water total, is the accumulation, the total water flowing in, and the orange part is the total water flowing out. The orange part is total water flowing out. Okay, so the blue part is the water flowing in. That makes the amount of water go up. The orange is the total water flowing out. It makes the total amount go down. There are really two ways of doing this question. Two ways. We can either do the total amount of water in minus the total amount out. So the area. We can either do two methods. We can find the area in minus the area out. So let's try that first. The area in minus area out. Going back to our graph, what is the area of water, the accumulation of water flowing in? So flowing in, we have a rectangle and our triangle. That's the rectangle is 6 times 4 is 24. The triangle is 6 times 3.5 divided by 2. So 1/2 of 6 times 3.5. Okay. That's from 0 to 6. Yeah. Okay. When we do that, we get 24 plus 3 times 3.5. That gives us 34.5. So how much water has flown in? 35 milliliters. Next, the water flowing out, the orange part. So let's go to the orange part. With the orange part, the water flowing out, the area of the rectangle is 1 times 6, which is 6. The triangle is 6. It's 1/2 times 6 times 4.5. 1/2 times 6 times 4.5 is 1/2 times 3 times is 3 times 4.5. Let's write that out. So 6 plus 1/2 times 6 times 4.5. That's the area of the triangle. So if we do that in the calculator, 6 plus 1/2 times 6 times 4.5, that's 19.5. 19.5. So how much water came in? 35 milliliters. How much water left? 19.5 milliliters. Well, we started with 30, right? We started with 30. Plus, we got 35 milliliters flowing in. Minus 19, the flowing in is 24 plus, it's not 35, it's 35.5. Let me be more careful. I wrote 35 when I said 35.5. Okay. Flowing out is 19.5. So we have 35 point, so we started with 30. We got 35.5 milliliters flowing in. We lost 19.5 milliliters flowing out. 30 plus 35.5 minus 19.5. That's equal to 46. Let's go to 46. So how much water is there at t equals 6? We have 46 milliliters of water. Okay. Another way we can thinking of this here, the way I did it was area in minus area out. What I could have also done is I could have done the function for in minus the function for out. So here's the function for in on Desmos, the function for out. We have two lines. When I subtract, this is, I can do in minus out and then find the area of that function. We'll see that in the next example. So part B, is the amount of water in the tank increasing, decreasing, or staying constant? Well, notice that the in is always higher than the out. So more water is always going in than coming out. So the area is always increasing. So the amount of water in the tank is increasing. Okay. And that makes sense. We start with 30. After 6 seconds, we have 46 milliliters. Okay. Example 4, more on net change. We have a supermarket. Some people are coming in. Some people are leaving, going out. From 0 is less than t is less than 4 hours. People enter. They come into the supermarket at a rate of f of t equals 20 for the first hour, and negative 10t plus 30 for hours 1 to 4. 1 is less than t is less than 4. No one enters the supermarket after t equals 4. When no one enters, that means f of t is equal to 0. After t equals 4, that means that f of t is equal to 0 for t is greater than 4. Okay? So that's the people coming in. Let's look at that function. That makes sense. So in the first hour, a lot of people are coming in, and then from 1 to 4, the number of people started going down in a straight line. Okay. From 3 to 6, from 3 is less than t is less than 6, people leave. They go out of the supermarket at a rate of g of t is equal to 10t minus 20 for between the hours 2 and 5. And g of t is just equal to 20 for the hours between 5 and 6. Let's graph this. When we graph this, what do we get? We get this. So at the beginning, nobody's leaving in the first 2 hours. And then more and more people are leaving. The rate of change is actually increasing constantly between 2 and 5. And then the rate of change is constant between 5 and 6, is 20. There's no one in the supermarket at t equals 0. Okay, so part A. How many people are in the supermarket at t equals 2? There are two ways to do this. One way is to find the area in minus area out. That's what we did in the last example. The second method is to do the area. So in other words, we want the area of g of t, area of t, f of t, minus area of g of t. That's the first method. Second method is we want the area of the function in minus out, which is the area of f of t minus g of t. We will get the same answer. Okay. Let's use both methods to do part A. Actually, it's going to be the same. We'll use both methods to do the other parts. How many people are in the supermarket at t equals 2? Well, from 0 to 2, nobody is leaving. Okay. So from 0 to less than t to less than 2, no one is leaving. So the number of people is just area, it's just the number of people in, which is equal to the area of f of t because all we care about is the number of people coming in. No one's leaving in the first 2 hours. What's that area? Well, here is our area of f of x under the graph. We want x equals 0 to x equals 2. Okay. This is a trapezoid. But I think the easiest way of doing this one is to recognize that in this graph, every square represents the x-axis goes up by 1, the y-axis goes up by 10. So what's the area of this little square? Well, it's 1 times 10, which is 10. This is 10. So every box has an area of 10. If that's the case, we want the area from x equals 0 to x equals 2. So it's this region, from x equals 0 to x equals 2. So let's add them up. So we know that this is going to be 10 plus 10 plus 10 plus 10 plus 10. And we have a triangle, which is half of square remaining, half a rectangle remaining. So that's 5. So how many people entered? Well, 55. So the area is going to be 55 people. Okay. Part B. How many people are in the supermarket at t equals 4? Well, that's going to be it's going to be the area of f of t minus the area of g of t from 0 to t to 4. Let's find the areas. So let's look at the end part. From 0 to 4, we have from 0 to 2, we already got our 45. What else do we have? We have 10 more people in this square, 5 more here, and 5 more here. So it's 10, 20, 30, 40, 50, 60, 70 people came in. 70 people came in. We're not done yet. We have to figure out how many people left. How many people left? Well, we want from 0 to 4. Here's our function for people leaving. We only want 0 to 4, so only this region. Nobody left from 0 to 2, so it's really just 2 to 4. Again, each area is 10. 10 plus 5 plus 5, so 20 people left. So from t equals 0 to t equals 4, 70 people came in, 20 people left. 70 minus 20 is 50. Of course, we started with no one, so that's why if 50 people, net people came in, 50 people are in the supermarket at t equals 4. Finally, part C. How many people are in the supermarket at t equals 6? Okay. From 0 to 6, well, here are the number of people who have come in. Here are the number of people who have come out. They have the same area. They're symmetric. So clearly, the number of people in, which is the area, equals to the number of people out. So people in minus people out is equal to 0. It has to be equal to 0. And that makes sense. Everybody who entered the supermarket has left by t equals 6. Okay? What were those? Area in minus area out has to be 0 if the two areas are the same. Now, instead of doing the area of f minus the area of g, we could have done the area of f minus g. If this is f and this is g, the blue line is f, red line is g, then f minus g looks like this. Okay. So to find the area for f minus g, we will do this part, which is positive because it's above 0. And this part, because people are now leaving the supermarket, This is the area below the curve, the graph, and that's negative. Add sum these two areas together, the positive and the negative, and we will get 0. Okay. So accumulations can be positive and negative. When the accumulation is positive, that means the total is going up. When the accumulation is negative, that means the total is coming down. So if we were to graph the people in the supermarket, we know it's going up, and then it starts coming down. Start at 0 and it ends at 0. All right. That's it. Let's summarize. The big idea here is, given the graph of how fast something is happening, the accumulation is the area of the graph under the rate. If the rate is this line, the accumulation is this area. In this lesson, we have stuck to things we can do with algebra and geometry with straight lines. In the next few lessons, we will want to figure out the accumulation if our function is a curved line. We will have to find the area under the graph for curved lines. So that is what's coming up. Okay?